Hi, and welcome to this second video on the probability section from Year 2. The first video was just recapping the Year 1 stuff. Let's now get into the Year 2 content. So what we're going to be doing is having a look at conditional probabilities and understand what those are. And in this first video, we're going to have a look at how that works with two-way tables, Venn diagrams, and we'll do some work on just using the probability formulae that we saw in the previous video. And then the final video will be on doing something similar but with tree diagrams. So let's have a look at what conditional probability is all about. So let's start off with an example. We've got here a Venn diagram showing all the students. Each dot represents a student there. And we've got some students study French, that's set F. Some study German, that's set G. Some study both, that's the bits in the middle. And then some don't study either French or German. So let's just take that information now and let's just plonk it into a two-way table, because it makes life a bit easier to see what's going on if you have a look at a two-way table. So if we fill in our two-way table, the ones that study French and German, and from using our set notation, that's F intersection G. So we've got, there they are in the middle there, three of those. Studies French but doesn't study German. So that's these blue ones here, French but not German. So that's F intersection not G. And so that gives us 6 there. And so we've got a total of 9 students studying French. Let's have a look at the ones that don't study French. So these are the ones that don't study French but do study German. So that's not French, and at the same time they do German. So there's 4 of those. We've got the ones that don't study either, which is complement of F intersection complement of G. So that's the 2 students. So therefore we've got the number of students not studying French, which is 6 of those. And then if we just kind of add up our columns, because we've got these basically, the rows are the ones studying French, the ones studying German, we can see we've got 7 students studying German. So there they are, there's my 7 students studying German. And then we've got 8 students, 1, 2, 3, 4, 5, 6, 7, 8, who don't study German. And so you can see that my tallies, my columns here, there's 15 there, 15 there, that all adds up. So my universal set, I've got 15 students in it. Okay, nothing new or particularly challenging thus far, but let's just have a look at what we now mean about conditional probability. So let's just take a really simple example. Let's say we want to know the proportion of students that study French. Then we're looking at those students that study French compared to the entire class. So we want the probability of studying French is going to be 9 students study French out of the entire class, which is 15. So that's the number of French students over the number in the set. Okay, and again, nothing particularly exciting about that one. But if we change it slightly and say, well, okay, we've got some initial information. We know something beforehand before we start looking at these French students. And what we're saying is we want to know the probability that students study French given that they also study German. Now, it's the given that is the conditional part of it. So given that they study German, what's the probability that they're studying French? Now, in this particular case, we're not looking at the entire set now. What we're looking at now is just the students studying German, because we are given that we know they study German, and then comparing that essentially to how many of those students study French. Now, the notation we're going to use is that straight line there. So what we're saying is the probability of F given G. Probably they study French given that they study German. So this is the new bit for Year 2, this notation here. And we can see that in order to work that out, let's just start off with the denominator first of all. Given that they study German, we are only interested in the German students. So those 7 students there. And now of those students, which are the ones that are studying French? Well, that's going to be the 3 in the middle here. And you can see if you look at what I've got highlighted here, what we've got is the numerator is F intersection G, and the denominator is just G. And I've got that here in terms of numbers of students because that's the way it's set up. But exactly the same thing will work with probabilities. And what that does is gives us rise to a formula that says for any 2 events, A and B, I used French and German in my example, but just in general terms, A and B, the probability of A given B is always going to be the probability A intersection B over the probability of B. That's basically the same setup as we saw here. Okay, and this is the formula that you're going to need to be familiar with and you're going to work with. But underlying that formula, because for me when I look at that formula I kind of lose track a little bit of what I'm actually thinking of. It's that idea of, okay, let's just think about the students initially. Which subset of our whole set are the ones we're interested in. In this case, it was the German ones. And then out of those German ones, which are the ones we want to know about, the ones who study French. So I often find it easy to think about the denominator first and then the numerator after that. So let's have a look at an example. So this might be a question that you might pick up from an exam paper. So we've got events C and D. We're told we've got probability of C is 0.65, D is 0.4, and we're given the value for the intersection as well. Now, here's what I mentioned in the previous section, the idea of first of all showing that these events are not independent. So if we're going to show that they're independent, we've got to show that the intersection is the probability of C times by the probability of D. And so if we do that, probability of C times by probability of D times those two things together, we can see we've got a value of 0.26, but we're told in our question that the intersection value is actually 0.15. So that's not equal to the intersection, so therefore they are not independent. Okay, that was a reasonably simple and straightforward one, but hopefully it gives you an idea of what you might be asked and how you're going to be asked to use this formula here. Right, let's get into the nuts and bolts of this, which is the given part of it. So you can see B part 1, we've got the probability of C given D. And we know we've got to do a calculation that uses the fact that something is given. So we've got our straight line here. So straight away, let's pick up the formula, which is probability of C given D is probability of C intersection D over the probability of D. Now, before I go too much further, it's something I probably should have mentioned earlier, which is you are actually given this formula in the formula book, but you're given it in a slightly different form. So what you'll get would be probability C intersection D, although in the formula booklet's A and B's, is probability of B times the probability of C given D. So that's the version that you get in the formula booklet, but it's, the same formula, it's just a rearranged version of the same thing, so not a biggie, but it is there. And let's say if you look in the formula booklet, as bizarrely, they give you, kind of probability A, sorry, not A, is 1 minus probability of A. Why they feel the need to give you that one, I've got no idea. But as with all things, it's always a good idea to make sure you know exactly what formula you get and what you don't, so you know what you're doing. Okay, so you will get to know the formula, but it's there for you in the formula booklet if you need it. So that's the formula that we're going to use. So we can see we've got probability C intersection D, we've already got that value. Probability of D, we've already got that one. So it's a simple case of just banging the numbers into the formula. And there you go, there's the first bit done. Now we don't necessarily need to, but while we're at it, let's just have a look at what that looks like on the Venn diagram. So there's my Venn diagram, C and D, and again I'm going to start in the middle and work out. So there's the intersection, 0.15. I've now got probability C is 0.65, which means that bit there is 0.5. We've got the probability of D is 0.4, so with the 0.15 we've got there, that gives us that bit there, 0.25, and finally the bit around the outside, which is the complement of C or D, which is 0.1, and so there's the Venn diagram. And so if you have a look at it on the Venn diagram, we've got the given D, so there's, given that we're only interested in the bits in D, given that, there's a 0.4, what's the probability of C? It's going to be the 0.15, so you can see why that's working. So there we go. Right, on to this one. So a little bit more complex now. So we want the probability of D given that C, we know it's in C or D. So given C or D has occurred, what's the probability of D? Now let's translate that first of all into our formula. So what we've got now on the top is the intersection of the two bits that we've got here. So we want the intersection of D with C or D. So that's the first bit. And then on the bottom, we want that bit from our previous formula, so we want C or D on the bottom. So that's what our equivalent version of the given formula would look like. So to figure this one out, let's go to the Venn diagram because it's definitely much easier to see what's going on from the Venn diagram. So the first thing we want is in D and in C or D. So let's have a look at it's in C or D, which is the yellow, but also we need it to be in D, so that's kind of the green bits. So we can see there we've got in D and in C or D is going to be 0.4, which is basically essentially in this particular case it's just in D. But we've got to compare that with the probability it's in C or D. And so the bit on the bottom is in C or D is going to be that bit there. So all of the yellow, which is 0.9. So our probability becomes 0.4 over 0.9. That's 4/9, which is 0.44 recurring. And there we go. And finally, part C, we want the probability that it's in C given that it's not in D. So in C given it's not in D. So here we go. Let's go for our formula first of all. So we want to be in C intersection not D over the probability of not D. Now I haven't shaded the Venn diagram. Let's just have, in this case, let's just have a look at what's going on. So in C and not in D. So it's got to be in C, but at the same time not in D. So that gets to that bit. So that leaves us just with the 0.5. And for the denominator, we just need not in D. So everything that's outside D. So D is here. Outside D would be the 0.5 and the additional 0.1. So we've got 0.6 on the bottom. So it's in C given it's not in D is 0.5 divided by 0.6. So that's 0.83 recurring. And there we go. So on we go, and let's have a look at an exam style question. So this is similar to what you might get in an exam, but kind of a bridge. I just picked out the relevant part to what we're talking about here. So we've got some information about probabilities. So let's just first of all have a think about what we've got. So we've got probability to play football, probability to play cricket, and the probability to play football given that they play cricket. And the first thing is like we want probability that plays football, cricket, or both. So what is that in terms of our set notation? Well, hopefully we're able to realise that we're looking for F union C. So if we want F union C, let's start off with our formula. And we know the formula for that is that. Now we don't know if it's mutually exclusive or not mutually exclusive. But if these things are mutually exclusive, that thing there would just be 0 and we're left with probability F plus probability C. So let's just work with the whole formula and then we know we're covering all our bases. Now in this form, we've got probability of F, we've got probability of C. The bit we're missing is the probability of F intersection C. So we've got to figure out where to get that from. And the one piece of information we haven't used yet is this bit here. In fact, the probability given they play cricket is 9/14. So let's see what happens with that formula. So let's pick our given formula. There it is. And you can see that the bit we need to find this F intersection C is sitting in there. So we can use this formula to find the missing bit. So let's first of all do a little bit of rearranging. So let's move that probability of C off the bottom of the fraction and turn it into a product. And now we've got enough to be able to put the information into here. So we've got the probability of F intersection C is going to be 9/14 times by 3/4, which is 27 over 56. So now I've got everything I need to be able to go back to this formula here. So let's just bang all our numbers in. There they go. And so just put them into the calculator, work them all out, however you want to do it. There we go. Probability of F union C, 55 over 56. Right, final example I'm going to do. We've got probability of Q 0.37, probability of R, and we've got probability of Q intersection R. And the first thing is find not Q given not R. And again, I personally prefer always to go to a Venn diagram with these kind of things. It's kind of the scaffolding I need to help me function. So let's have a look at what we can put on here. So we've got Q intersection R. Let's start in the middle, put that in. So that given probability Q is 0.37. So that's that bit there. So we've got 0.37 there in Q. And the same principle to find the leftover bit for in R. It's 0.25 to give us the 0.42 in Q. And then whatever we've got left is going around the outside. So that's the 0.38. So there's my Venn diagram. And we want not Q given not R. So there's our conditional probability formula. Not Q intersection not R over not R. So we want not in Q and not in R. So not in Q and not in R. Well, that essentially means it's just going to be that 0.38 bit there. So that's that. And we want that over the probability that it's not in R. So not in R. There we go. There's the bits there in R. So not in R is going to be those two bits there, the 0.2 and the 0.38. So that's where we get the 0.58 from. And there we go. There's the probability of not Q given it's not in R. We're now chucking a third event into the mix. And we've got event S with the probability. And we're given some information about Q and S. We're told they're mutually exclusive, and we're told that R and S are independent. Let's first of all focus on the mutually exclusive part of it. Well, that's telling us that Q and S are not going to overlap because they're mutually exclusive, but we're not told anything about R and S, so we're going to assume that they do overlap. So what I'm going to do is put my extra circle in there. Now let's use the second part of that, which is events R and S are independent. So if we've got independent events, we know that. And so the intersection here is probability of R times by the probability of S. And we've got those two values. Where are we? There we are, the 0.42 and the 0.2. So that straight away tells us that intersection there is 0.084. So that can go on my diagram there. We're trying to fill out the rest of the Venn diagrams. Let's have a look at what's going on. Well, nothing is changing with regard to Q and R. So that value there is still 0.2. That one is 0.17. Now things are going to change a little bit because we need the total probability of R is going to be 0.42. So what have we got left over to go into that middle bit there? Well, that's 0.166. And then we've also got the fact that probability of S is 0.2, which gives us this section here, which is going to be 0.2 minus 0.084, so that's 0.116. And then the final bit again is anything that's not in Q, R or S. So let's add up all those bits there, take them away from 1, and we get 0.264. So there's our Venn diagram sorted. So that's part B done. And finally, part C, we want the probability that it's not in R or S. So R is there, S is there, not in R or S. It's going to again be the 0.2 and the 0.264. Those two bits there. Add them together. And there we go. There's our answer, 0.464. Okay, so that's basically all our work done on Venn diagrams and conditional probability. One more thing to go, which will be the next video, which is how the conditional probability stuff looks like on a tree diagram.